But let's take a look at this reaction here. We have copper plus nitric acid. Copper plus nitric acid, this looks like A plus Bx, correct? A plus Bx. And so if it's A plus Bx, what do we form? We're going to go from copper, we're going to form AX, which would be copper nitrate. And so copper nitrate, what charge on copper should I put? +1 or +2? What charge on copper should I put? +1 or +2? +2. How do I know it was from the chart? And so copper nitrate would be CuNO3 and then this would be AX, copper nitrate, plus B. B would be H. What's the element H? H2, hydrogen gas. Well, let's see if there's a driving force. So we'll just do the activity series for this. We're going to compare A and B using the activity series. So the activity series starts with lithium down here. We go up, here's hydrogen. We're comparing copper and hydrogen. Which one's more active? More active is the one closer to lithium or farther from lithium? Closer. In other words, hydrogen's more reactive. What would you rather have, a pocket full of hydrogen or a pocket full of copper? Probably copper. It's more stable. Plus it's worth something. But anyway, going back to this, we expect no reaction because we're going from this less active, more stable, to more active, less stable. In other words, we're going to a stronger reducing agent, starting off with a weaker reducing agent. Copper is a weaker reducing agent, so let's react. And so what this means is there's no driving force, and therefore no reaction. But we should say no reaction for what? No. No reaction for the single replacement pattern, A plus Bx. We need more patterns. Do you want to memorize more patterns? Not really, probably not. This is no reaction for single replacement. There is a reaction for redox. There is a redox reaction. But the pattern is much more complex. It's the A plus Bx yields CX plus G plus H plus I, whatever. You know, it's more complex. And so, in other words, it failed. Why would I suspect single replacement fail here? Because I look at the acid. What kind of acid is that? Is that a mineral acid or is that an oxidizing acid? It's an oxidizing acid. If we're dealing with a mineral acid, then no problem. If I had just simply switched this to HCl and we got no reaction, then you're good. That would have worked fine. But since it was an oxidizing acid, that's Let's take a look at this reaction here. Potassium. What's the symbol for potassium? K or K plus? K. Is it solid, liquid, gas, or aqueous? It's a solid potassium, the element. Is carefully added to a sodium chloride solution. Hey, this is A plus Bx. What was A again? reducing agent. Hey, potassium is an excellent reducing agent. It's number 2 on our list. So far, so good. B would be our oxidizing agent. Sodium ions are oxidizers, and chloride's a very weak reducer, and so potassium metal would be much better. And so this looks like single replacement works. What forms? Well, AX. AX is potassium chloride. Potassium chloride is KCl plus B. B is just sodium, the element, which would be sodium metal. And so let's compare the two elements and see. We're going to compare potassium and sodium. So the most active is lithium. So potassium is more active than sodium. So we're going from more active to less active. More active to less active, that means there's a driving force. Did we finally have success? Did we have success with single replacement worked, right? Single replacement worked. No, it didn't work. It failed. Single replacement failed. This is another example of failure. But hey, it's not fair. Well, sometimes nature's not fair. Sometimes nature's going to pick all the failures and give you all those, so single replacement's never successful. Why did it fail? Why did it seemed to have worked, but it failed. Why did it fail? Everything looks good. The strongest reducer present, well, I have potassium and chloride. Potassium is way better than chloride. And then I have sodium as my oxidizer, and chloride's not even an oxidizer. It doesn't occur on the... And so this looks like it should work. But it failed. It failed. Do you know why it failed? Because it failed because there's another oxidizer that's stronger than sodium ion. Do you know what oxidizer is stronger than sodium ion? And it's not even written here. That's why everybody misses it. Everybody misses it because it's not even written here. What is it? It's water. Yeah. Water. And so this is the wrong reaction. Even though we did get a driving force, this is totally wrong reaction. This is not what we're going to get. And so what are we going to get? What we're going to get is this. We need a different method. And so again, single replacement is great because it's easy. But we have to beware of all the potential failures of the single replacement method. And so I don't want to memorize this. I don't want to memorize single replacement is good except for this, and list all the scenarios. I'd like a different method. The different method is called the chart method. It's the redox chart method. And the redox chart method, we don't even have to bother with memorizing any exceptions. This is a more general procedure. And this general procedure is very similar to the acid-base procedure. First we inventory. Well, we did that for acid and base. And then we find the strongest oxidizer and the strongest reducer. We don't have to memorize the chart, we just look it up in the chart. Just like in the acid-base, you had to find the strongest acid and the strongest base. How did you do that? You looked at the chart. How do we find the strongest oxidizer and the strongest reducer? We look at the chart. You're going to be given the chart. And so you don't need to know the chemistry. You don't need to know why it's the stronger. You just need to be able to position it on the chart. And then we're going to combine the strongest oxidizer with the strongest reducer by adding up those equations that are written on the chart. We've got to make sure the electrons balance and then simplify. This method yields the NIE, the ionic equation. And so rather than look at it more, we should just do an example of this. Let's do the example here. And then we'll end with this. And then let me talk about the lab. So if I inventory this, potassium and sodium chloride, potassium solid, sodium chloride aqueous, what do I have? I have potassium metal, I have sodium ions, I have chlorine ions, and I have water. And then all I have to do is consult the chart. And so I look for potassium. Okay, potassium occurs with lithium. These are the reducing agents, lithium being the strongest. So potassium is a reducing agent. Potassium does not occur on the right side. This is potassium ion. Potassium ion is not potassium. Totally different. And so there's no other potassiums here. And so potassium is only a reducing agent. Sodium ions. Sodium ions are over here on the left. These are oxidizers, the strongest being fluorine up at the top. Sodium ion is not sodium metal, and so these are oxidizers. Sodium ion is an oxidizer. Chloride, chloride's way at the top on this side. You see bromide up there, chloride's even higher. Chloride is a reducer. Water occurs on both sides. So water is an oxidizer and a reducer. And so I have two oxidizers. Sodium ion versus water. Which one's stronger? So I got to figure out which one's stronger. Well, the strongest oxidizer is fluorine at the top. And so here I have water, here's sodium ion. Which one's stronger? Sodium ion or water? Water. Water is closer to, in fact, water is, where would I position water? Up here. Yeah. And so water is stronger than sodium. Water belongs there. And so this is why single replacement failed. You were the director of this reaction, and you told sodium to be the oxidizer, but water comes in and takes over that role. Why? Because it's just nature. You can't dictate it. That's what we're doing. We're trying to dictate to nature what you're going to do. You're going to do this, you're going to do that, but nature's just going to do the way it wants to do. Right? And so that's the problem with the single replacement. Okay, which one's the strongest reducing agent? Well, lithium's at the top, followed by potassium. Potassium is the second strongest, so this is going to be the strongest reducing agent. These other ones are going to be weaker. And so the reaction is going to be between potassium and water, not between potassium and sodium. And then all we do is we copy down the reactions. And so for water, we'll copy it down. This. And so I'm just going to copy that down. 2 waters plus 2 electrons yields hydrogen gas plus 2 hydroxide. Okay. Then I'm going to copy potassium. But potassium, it's potassium as the reactant, not potassium as the product. So if potassium is the reactant, then we're going to reverse this. If I reverse this and make potassium the reactant, I'm going to get potassium solid goes to potassium ion plus an electron. And so this reaction is reversed from what it's over there because potassium is a reactant, water is a reactant. Now when I look at the electrons are not balanced. I have 2 electrons that I need, and I'm only producing 1 here. And so in order to balance it, we need to change the coefficients. To change all the coefficients, I'm just going to multiply the whole thing by 2. If I multiply the whole thing by 2, I get 2 electrons here. And then I'm going to add them up. And so I get 2 waters plus 2 electrons. These 2 electrons will cancel these 2 electrons, so I'm going to eliminate those. Plus 2 potassium solids. So 2 H2O liquids plus 2 K solids is going to produce H2 gas plus 2 hydroxides plus 2 potassium ions. Now we determine the driving force. We're going to use the conjugate relationship for the driving force here. Water is an oxidizer. Water is taking electrons in this top reaction, so that's the oxidizer. If I reverse this top reaction and go backwards, then hydrogen and hydroxide lose electrons here, going backwards. So this is the reducer. And these are called conjugate pairs. Oxidizer, reducer, conjugate pair, Ra. Likewise, potassium is my reducing agent, because going forward, I lose electrons. However, if I go backwards, then potassium ion is my oxidizing agent, because that's taking electrons. And so I can assign these. Water is my oxidizing agent. Potassium is my reducing agent. Hydrogen in hydroxide is my reducing agent. And potassium ion is my oxidizing agent. And then I compare the two oxidizing agents, water versus potassium ion. Which one's a better oxidizing agent? And so here's water, belongs here. Here's potassium ion. So water is a better oxidizing agent. In other words, water is a stronger oxidizer. Potassium ion is weaker. That means the reducing agents must follow. So potassium metal must be a stronger oxidizer than what? Not oxidizer. Potassium metal must be a strong reducer than hydrogen and hydroxide. And so potassium metal is a stronger oxidizer than hydrogen and hydroxide, which is here, and that's correct. And so we're going stronger to weaker. And so this is our driving force. And so the reaction here, there's going to be a reaction, but the reaction is not as expected by single replacement. The reaction is between potassium and water, not potassium and sodium chloride. Okay, so that was a trick. A trick. And so the thing is, what we want to do is we want to just learn a little bit more, and that means we don't have to memorize as much. We don't have to memorize all the exceptions. It's a little bit more work, but we'll see. Also, we'll get a better feel for the reactions. All right, any questions on that? All right, so for today's lab, what we're doing is we're doing the experiment 6. Experiment 6 part A, I'm going to do that as a demo, but not today. We're going to do parts B through E today, and you're going to do them. Parts B through E.
I did that trying to get to my backpack earlier. It was a little bit. Wait. I like how you said that the monitor. So you're going to do the long experiment class?
No. This is part A. You're going to do this. Do you see this? This is copper 2 sulfate pentahydrate. How can I get rid of the waters? How can I get rid of the water? Heat it up. They call that a decomposition, but I don't call that a decomposition. I call that a physical change. All we're doing is we're driving the water out of the crystal. Nothing's changed. It's still copper 2 sulfate, right? It's just dehydrated copper 2 sulfate. And so that to me is a physical change. So for example, if you ate dehydrated pizza, was that a chemical change or a physical change?
I just sounds really sad.
Yeah, it's a physical, because if you rehydrate that pizza, in theory it should be the same pizza as you had before, right? Whereas a chemical change would be if you burnt it. If you burnt the pizza, then obviously that's not the same. Okay, this is a decomposition though. Do you see what this green stuff is? This green stuff is copper 2 carbonate. And so what we're going to do is we're going to heat it up. We're going to heat it up and get it hot and hopefully decompose it. What will it decompose into? Will it decompose into copper metal? Possibly, if we get hot enough. Will it decompose into diamonds and oxygen? What do you think? Maybe not diamonds, but maybe graphite and oxygen? Actually, there's no water here at present. And so Or what do you think would decompose into copper 2 oxide, solid, and carbon dioxide? Does that look reasonable? Yeah. And in fact, you can see that's what I did here. Do you know what this black stuff is? Copper 2 oxide. And so what I did was I heated the green stuff and it started to turn black. Well, how do I know that's copper 2 oxide? Well, one, the color. You know, copper 2 oxide is black, right? And it seems reasonable. And two, I can figure out the gas that's released from this. I can do a simple chemical test for the gas. And the simple chemical test is, I'm going to take this stuff. This stuff is already getting contaminated. This is called lime water. Lime water likes CO2. If I exhale on this, I get a precipitate. Because what happens with lime water is this. Lime water, which is calcium hydroxide, reacts with CO2 gas to form calcium carbonate and water. This is an acid-base reaction, Lewis acid-base. And so obviously this is going to start becoming cloudy because we have CO2 and air. And so it's turning cloudy. So what you want to do is you want to get the clear stuff in the middle. Don't take it off the surface. Try to get it off the middle because the surface of this is going to get a film of calcium carbonate from reacting with CO2 and air. And so we want as clear of a solution as possible for our calcium hydroxide. So that's pretty clear. Do you see that? Okay. Phenolphthalein. Do you know what phenolphthalein does? Phenolphthalein turns pink if there's hydroxide present. And so if I put a drop in here, will it turn pink? Yes. If I put a drop in here, it's going to turn pink because there's hydroxide present. Okay, you're going to work with a partner. I don't have a partner, so I'm just going to do this by myself. But what you're going to do is you're going to heat this up like this. What you want to do when you heat this up is move it around, because if it starts going out of control, be careful. And another thing you want to do, this happened today because a lot of people weren't getting any gas bubbles. They weren't getting any gas bubbles because the cap was loose. And so all the CO2 was escaping the side. So you want to make sure the cap is secure before it's hot. And so my cap is on there tight. I'm going to start heating this up. But can you see the CO2 coming off? No. But let's see if I can detect it using some bubbles. Now do you see the CO2 coming off? It smells like gas. So I'll just keep heating this up. Once you think, okay, this is staying pretty well in control, then you can heat it up more vigorously. Need a better flame. What's happening to the pink color? Yeah. Okay, what happened to the pink color? It's gone. And do you see it's cloudy? What's that cloudy stuff? Calcium carbonate. And so this means that this is decomposing. This is decomposing into copper 2 oxide, which is the black stuff. This is what your pennies are going to look like after a long time. And CO2. Okay. So we're good. Okay, so now I got a cloudy precipitate in there. So I wanted to demo that. Watch out, this is very hot. You don't want to touch it. And this is very hot. So don't touch it, otherwise you get a burn. Okay, what other reactions are we doing? Oh, we're going to do another test for gas. The other test for gas is this. We're going to take some zinc. What happens if I mix zinc with HCl?
we get hydrogen gas. What happens if I mix magnesium with HCl? If I mix magnesium with HCl, the same thing is going to happen. Do you see the bubbles there? Maybe that's a little bit too violent.
Oh.
That gas that's being generated is not CO2 gas. That gas that's being generated is hydrogen. And so what I'm going to do here is this. There's a test for hydrogen gas. Do you know what the test for hydrogen gas is? CO2 gas is used in fire extinguishers. Right? So if I put a match to CO2 gas, what's going to happen? It'd put it out. But if I put a match to hydrogen gas, what's going to happen? It's going to explode. You don't want to point this at you. You want to point it away from you. Watch out for false, because there could be a delayed explosion. So you might be poking around. What's going on there? And then it explodes. That's usually what happens. But you know what? I was too slow. So this time I'm going to be a little quicker here, because the hydrogen gas dissipates pretty fast. Okay, now I'm bubbling. That's a lot of hydrogen, right? And this time what I'm going to do is I'm going to just kind of cap it so hydrogen gas doesn't escape as quickly. Since you have a partner, you probably don't have to cap it like this. Okay, now let's see if this is successful. Ready? All right, let's try that one more time. That was not that impressive.
I was like, well, okay, I thought.
Well, we don't want a big explosion, of course.
Kind of.
All right.
These are almost carbide. Pretty high.
Okay, did you see it?
No.
No?
What are we supposed to see?
You didn't hear that?
No.
No, I heard it. All right, you didn't hear it. I'm using the wrong HCl for this. You got to be careful, because this reaction is getting a little bit too violent. I'm using the HCl that I have, which is 12 molar, so it's a little bit too concentrated. You might smell it. Do you smell it? So I'm going to just add a little bit of water, dilute it down. All right, can you see I'm bubbling the gas here? There's lots of bubbles forming. And this time I'm going to try to trap it. I didn't put my thumb on there tight enough, probably. You don't have to put your thumb on here if it's generating gas. But I'm going to. Okay, let's try this one more time. Oops. Ooh, this is very hot. Watch out. Ouch. It's very hot from the heat that's generated. Did you hear that? Did you see that? Yeah. All right, there it was. It's still generating hydrogen. Let me try that one more time. That still wasn't that much hydrogen, but there was a little bit of a pop, right?
Oh, that's cool.
Oh, actually, this is still.
I don't see it.
All right, when you do yours will pop a lot louder, because I'm using 12 molar HCl. It's too high concentration. There's too much HCl in there. Okay. All right, any questions on that? All right, let's talk about the hazards in this experiment. Hydrochloric acid, watch out for that. You know, if you do spill some. Lime water is not too bad. Copper, not too bad. Zinc, sulfate, not too bad. Silver nitrate. Silver nitrate's bad. Do you know why? Silver ions are a moderate oxidizer. Silver ions, what they do is, do you see the black stains on my fingers?
Yeah.
Well, that's from the pen, and those wash off. But if you get black stains from silver nitrate, they don't wash off. I had a student years ago, she had a job interview right after class, and she had silver nitrate stains all over her hands. And she said she was washing her hands for 25 minutes and the stains didn't come off. They aren't going to come off. You have to wait until the skin sheds because you have tiny crystals of silver in your cells, basically. And so don't, watch out, don't touch the silver nitrate. Don't get any in your eyes, too. All right, what else do we have to watch out for? Lead. We have to watch out for lead 2 nitrate. If you do spill lead 2 nitrate, wash it off immediately. If you happen to drink some lead 2 nitrate or something like that, then you could be eligible for chelation therapy, in which you can use some sodium EDTA or some calcium EDTA. What would your preference be, sodium EDTA or calcium EDTA? Calcium? Yeah. Well, it depends on how high your blood level is. All right. So watch out for the lead. Obviously, we don't want to spill any. And that's about it. Okay. The rest are just, avoid contact. The silver and lead those are actually both heavy metals, so try to avoid contact with those. And silver stains things black. You know what nitric acid stains? You can tell if you spill silver nitrate on your hands because it's black and it doesn't wash off. You can tell you spilled nitric acid on your hands because it's yellow and it doesn't wash off. We aren't using any nitric acid in this lab, but if you see yellow stains on your hands, then it's probably nitric acid.
Are we skipping A since you're going to?
Yeah, you were skipping A, so go straight to B. You don't have to do these in order. All right, that's all for today's discussion. There's some loaner goggles up here. Goggles are required for this one. Oh no! What kind were they? Well, if you find a pair up in there, you can hold on to them for the semester if you want.
So my mom just got glasses last week, and she's been growing up because the way that they get transitioned from low to higher at the bottom. Yeah, and that reminded me of how I felt last week when we knew this and they were perfect. All right, so what do we do?
Do you need to go over there and get stuff?
Go over where?
Out here?
Stockroom?
Yeah.
This tube is actually on the back bench over there in a box. You don't need to check out anything. All the equipment that you'll need is back there, and all the chemicals you'll need are back there. So we don't have to go to the stock.
Can we bring chemicals to? No, we have to have key back there.
Yeah, you have to bring your test tubes back there.
Okay, do you want to take the table?
You might need matches. There are matches at the counter, so if you need some matches, go ahead and grab some.
Are you going to collect our papers, or do you want? Are you just going to check our notebooks?
I'm going to just check your notebooks, but I'm not going to check it today because today's too busy.
So,
Last day. Yeah,
So
next
you're going
day.
to check this and last one next Thursday?
This one I'm going to collect because you're going to write the equations for this one, the reactions.
Okay. So last week you said you were going to check our notebooks?
Yeah. This week, write everything in your notebook again, and then I'll tell you what we're going to do for the report. It's going to be a little bit different than the report sheet.
No, it's not checking this. Turn on the other one.